So we talk about this MVK mechanism. And so there was a work published in Oak Ridge National Lab. So what they do that they're using this sphere, and then using this called mechanocatalysis. They're using this many spheres. They apply a friction. They generate a hot spot between the surfaces, and they create this reaction. For example, you have ammonia, and under this stress or temperature, that the nitrogen adsorb, dissociate, and fill the vacancy about the titanium vacancy. And then they dissociate, and then they react with the gas phase, for example, that H radicals in the high temperature environment that form this ammonia process. So I think that if we were using a plasma process, the plasma is very efficient to generate H radicals and in gas phase in low temperature. And also that the plasma is very efficient to generate N atoms in gas phase that will dramatically accelerate this VK mechanism. So, all right. So plasma, as I said, and yesterday, they give you so much opportunities to do a non-equilibrium. So you have electrons impact with a molecular. You can generate ions electronically, vibrationally excited, radicals, and UV light. And this intermediate species is going to interact with a catalyst. For example, that you can, the photons generated in plasma, they can generate electron-hole separation and drive the photocatalysis. It can create a surface charge that could be negative or positive that build a very strong electric field near the surface that they dissociate the molecules or polarize the molecules. And you can also sometimes, if you microwave, you can generate a magnetic field. If the magnetic field is generated, is strong enough, you can change the spin of the molecules so that you can enabling that spin forbidden reactions in combustion. For example, you from a singlet to triplet, normally the spin forbidden, the reaction rate is very slow. But if you have a electromagnetic wave is strong, you could generate a flip the spin, and then you can making some reaction possible, which is, and you can also generate that the oxygen hole, this oxygen vacancy transfer that can enabling this new reactions on the surface. So what I try to say is that there's so much interesting things, and in terms of plasma, when you have materials come in, they create this kind of plasma surface interaction and create a lot of more interesting chemistries and physics, and many of them we don't understand. And right now, the good understanding probably in the gas phase yet, but in the surface phase, it's still very hard to understand. I think that one of the opportunities is some of you in this audience in the future take the lead, understand this part, and eventually and become a champion in this field. That would be great. And so I try to show you some examples about that plasma-assisted or aided chemical manufacturing, and starting from CO2 reduction, and then followed by ammonia synthesis, for example. So CO2 or hydrogen production become a big deal in terms of America's future. And this year, and the DOE just announced that they will fund $8 billion to produce hydrogen, and probably 9 to 10 hydrogen hubs in the United States. I never heard that there is research dollars at the level of about $8 billion. You know, it's just unprecedented. So the way of this, you produce hydrogen, you can using steam reforming, and from methane water to Cl and CO2 and water gas shift, and to making a CO2. So this process, if you're looking at that, the whole enthalpy process, they require 69 kilojoule per mole per mole hydrogen. So this is that industry. Probably more than 90% of hydrogen today in the United States is produced by this process. But unfortunately, this process produces CO2 as well. So therefore, this we need to find that alternative and to replace this CO2 emit and hydrogen production process from steam reforming. So then you can see there's water electrolysis. Today that is green hydrogen, and yesterday we talked at the dinner table. But the cost in energy is 286 kilojoule per mole per hydrogen. So that is by the about 4 times about the energy cost for that the steam reforming process. And what I'm to do, and in the Princeton Plasma Physics Laboratory, I lead a DOE Earthshot Center, is try to using a methane and to using plasma to produce a graphite materials or using methane with CO2 to form a methanol. And then this process, we can produce hydrogen with a 37 kilojoule per mole. You can see that the R cost in this way, probably 1/8 of the cost using. So therefore, that the methane pyrolysis using plasma might be electrification, might be a viable process and before transition fully to green energy, particularly for America, because we have a lot of natural gas, a lot of petroleum resources. So this carbon, you can be used for and battery anode materials, can be used for other carbon resources. So therefore, there's a lot of interest these days, particularly in Europe. If you go to Europe, that they has a lot of funding and to focus on how to make a CO2 into CO, and how to make a CO2 and methane making syngas, and how to using CO2 and water to make a syngas, and how to using CO2 and water to make a methanol. You look at the energy is 676 and twice more than this hydrogen production process. And also that is interested using CO2 and hydrogen to make a methanation. Maybe it does not make any sense for America, but I think that it maybe makes some sense for European countries. And this make a methanol, I'm pretty much interested in this process. You can see that the enthalpy change is exothermic. And this process, and if you have a lot of hydrogen produced from here, and you can make a methanol, and that could be electrified, the process, using e-fuels for engines. And you don't have to change the engine a lot. The methanol is easy to burn, and is much better than the ammonia to burn. So I'm one of the favor of this guy, and ExxonMobil also, and Shell, they kind of agree and in this direction as well. So ammonia synthesis, you can see that this is the exothermic process. In the, nitrogen will be oxidized and to form ammonia, and this is just like a combustion process as well. And you can have 2 ways to do so: directly a nitrogen-hydrogen reaction to form ammonia, or you can using a nitrogen and oxygen to form a NO. And from NO, you can make a nitric acid, you can make ammonia from that way. So the question that this reaction is that if you're running a chemical equilibrium using chemicals to synthesis, do modeling, so the maximum yield from nitrogen to NO is about 7%, around 2000 C. So if we can find some kind of game-changing ideas to make NO more than 8%, break down the chemical equilibrium, and you will be a champion in this field, right? How can we make NO from nitrogen and oxygen with 8% of efficiency? Remember here, 8%. So if any one of you can create 8% of NO from here, and write an email to me. So I think that so this is something very interesting. For here, if we can beat Haber-Bosch method by half, 50% of the efficiency compared to Haber-Bosch, you are a big deal too. Because this is making you electrified and distribute renewable ammonia synthesis. Even your efficiency is lower, but you are not high pressure anymore. You are not a CO2 and energy intensive. So this is that 80% of this, 50% compared to Haber-Bosch. Is there any, you can reach that, that is huge milestone. So if you're looking at first the same example, CO2 conversion to Cl. And this is one of the major research efforts pursued in European countries and using a plasma. So if you're looking at a CO2 energy diagram, they have ground state, you have a lot of vibration. So if you can pump in the vibrational state of CO2, and instead of electronic excitation of CO2 to dissociate, then you save a lot of energy. So really the question is that how can we, that they're using a electron process that vibrationally excited CO2, then dissociate in the CO and oxygen, so that make a CO2 reduction. So a lot of research has been pursued, and particularly in Europe. The United States is far behind. And I tell you that maybe 7 years ago when I went to Europe for conference, when I look at this, they are doing these reactions, I just was laughing. I said, why do you want to do this? And this is, it's not efficient. It does not make any sense. Because, but today you start to see America now is funding this type of research. It's because that is the urgency of decarbonization, right? I think that Europe is leading us in many ways in developing clean energy. So here's the energy efficiency, and here's the conversion of CO2 to Cl. So you can see some of the plasmas like this, and here, they can have a very high dielectric barrier discharge. They can have very high conversion of CO2 to Cl, but the efficiency is very low. It's only below 40%. And then some of the gliding arc we learned yesterday, microwave and radio frequency, and they have a high temperature. These are a very high temperature. And the energy efficiency is very high, but the selectivity is very low. So the question is really, how can we find something in this spot that has a high conversion efficiency and then a high energy efficiency? So that is the key questions about that CO2 reduction process. So there are some work about CO2 with dry reforming that using methane and CO2 to make a syngas. So this is one of the work about Nozaki, and Nozaki was, when I studied in Japan, he was a graduate student. So we met a good friend, and he's not in the combustion area anymore, mainly doing this kind of plasma chemical synthesis. So if you build this kind of a reactor, you can see this is that the plasma, high voltage electrode, and you have a layer about probably a dielectric barrier discharge of quartz, and you have this catalyst powders, and then you have an anode. I think that this is the yellow one is the anode. Is that the ground? Yes, is a anode. And then they generate plasma between this thing, and the catalyst basically is a fluidized bed. It's like so they try to understand how does the fluidized bed plasma discharge can reduce this CO2 into Cl. But you can see from this picture, not only they can form Cl and hydrogen, but also they form a lot of carbon black. So how do we suppress that the carbon black formation and use this kind of a CO2 and methane reforming is a big challenge. So to do that, you really have to control the electron energy distribution of plasma. So I don't think that this guy, they did anything. They just put a high voltage and then create all this. But we need ideas to control electron energy distribution to increase the selectivity and yield. So you can see this is that the CO2 conversion. They get to, depend on the catalyst temperature, and they can get to somewhere to 50% of conversion. And the selectivity can reach to 90% with that, what is the open solid circle? With that you can see that the fluidized bed, dielectric barrier discharge. And much better than the selectivity, much better than the thermal. Again, I think the thermal, they only drive it to equilibrium, and plasma, they drive it to non-equilibrium. So you can have a high selectivity, but the conversion ratio is still at 50% or below. So that is something, a challenge. And then the challenge you can summarize there, fluidized bed, and is much better than the fixed bed in terms of dry reforming. And there's high conversion can be achieved using DBT, but however, energy efficiency is bad because a lot of carbon formation remain a big challenge. So this is a problem. And the next thing that is the same group about the Kim and in Japanese Energy Research Institute and Nozaki, they're using a similar reactor. They want to understand that CO2 vibrational excitation with methane that form CO. And what they do, that this is the reactor, and this is the electrode, and there's another electrode on the other side that generates a discharge between the electrode. And this is the catalyst. They put a catalyst, and right behind the discharge, there's some flow of that CO2 and hydrogen, and then they will be catalyst. And you have an IR absorption spectroscopy to detect that species on the surface. And what the key question is that how does CO2 vibrational excitation affect the catalyst? And that is still an open question, and this paper was published in Jackson 2 years ago. So they try to understand that the catalysis with a PDGA catalysis, and then try to measure that how CO2 vibration affects the CO formation on the surface. So I try to show you results first, and then you can see this is the result is 1,000 divided by T. At 1.5 means about around 700 Kelvin. And you can see you plot that the year as a function of temperature, and you can say if you just heat that reactor, and then your activation energy is about 75 kilojoule per mole, right? So this everybody know. But if you're using a vibrational excitation for CO2, you get some data like that, 44 kilo per joule. So you are reducing the energy barrier by almost 40%. So that is significant. And so they compared of that the plasma with a different hybrid and a hybrid discharge and different frequency and different power. So what you see that this is that the reactant. This is the vibrational excitation of CO2, about 8 kilojoule per mole. About CO2, probably unsymmetrically stretching. And so if they do this excitation, what they found that 75 minus 8 equal to 67. The activation energy should be 67. However, the measured activation energy is 44. That means that not only this vibrational excitation level contribute to the reduction of energy barrier, but also there's some kind of new reaction pathways created that further reduce the energy barrier to make it 44. So this is very exciting. And I think this is the first experimental report that they're showing plasma non-equilibrium excitation of CO2 reduce the energy barrier experimental data. I never seen anything quantitative than this before. So I think that is the big, that's why the paper published in JACS. I think that is one of the big contribution in the society. So what they did that you can see, this is that the electrode, and is a 10 millimeter, 1 centimeter gap, and this is that the catalyst, and then the flow is going to that direction. The IR basically make an absorption. So this is the plasma discharge, and this is the catalyst, and then they adjust the distance between plasma and the catalyst, and to see how that is you see the asymmetric CO2 vibration affecting that catalysis. Here you can see it's heated, and this thermal. You don't see much about the CO formation. And then if you put a plasma on, you start to see a lot of CO is formed, and you turn it off, the plasma, and then you can see that it come back to the CO. So clearly the CO is sitting on the surface of that the PDCA catalyst, and then that is triggered by plasma. Without plasma, and you don't have it. So this is one of the dynamic measurement in terms of CO2 on the surface. And so they did this quantum chemistry calculations, and to see how that the CO2 with a H radical on the surface, and compare the reaction pathway and between LH, which is a Langmuir-Hinchinwood mechanism, and the ER mechanism, really pathways. And what they found that here, you can see that there is a surface reactions about HCOO with that H radicals production, and that created some kind of plasma hypothesis, like H adsorption assisted decomposition. This is called spontaneous. That means this two, this HCOO they dissociate, and then they form this CO plus H. They call spontaneous. Here, that is at the H assisted. So what they found that the LH pathways probably create a new reaction pathway to form the HCO and CO. So I think that this needs to be explained, even though that the quantum chemistry calculation is kind of supporting the materials, but not very clear that people really see the H on the surface, HCO is on the surface, and not much direct dynamics. So how can we develop an in situ diagnostics? It can see that the species on the surface, right? I think that is really need a next generation of diagnostics. And you have to be very fast, not using FTIR, this type of measurements. So what they say that, okay, the bending mode of CO2, and then the stretching vibration mode, they say that stretching vibration mode like this, the stretching like that, and they basically that contribute to reduction about delta E, but really does not create a new reaction pathway. So therefore, the EV is almost equal to the reduction about activation energy. But if that the CO2 is somehow bending mode, and then if it's like a bending mode like that, and they, not only that they reduce that energy in this way, but they create this way. This is something I don't understand, but I try to understand. I think that it is really depend on, if you have CO2 molecules, sometimes it's stretching, and sometimes it's bending. But if you have a catalyst, the catalyst is going to interact with the molecule. If you have bending mode, that you change your interaction between that the electron transfer, between that the catalyst to the molecules. For example, you're bending, you probably only can electron transfer from the catalyst to one of the oxygen atom. But you have bending, and two of them together, maybe two of the oxygen are simultaneously affected by the electron transfer process that it creates. I start to try to understand it, but the paper never explains anything. Here, that quantum chemistry calculations and will provide a good understanding, but why that the vibrational excitation is interfered. But unfortunately, the field of combustion chemistry, and they don't deal with this kind of vibrationally excited things, right? Unfortunately, that the chemical engineering people, they don't deal with this. They only deal with the surface. They don't deal with it. So this is an opportunity. I think that we have molecular dynamics, we have a DFT quantum chemistry, but very few people, they understand both. This is great opportunity for your generation. How DFT, high accuracy quantum computation, and how AI can come together to understand this kind of a non-equilibrium, particularly involving plasmas, electrons, and vibrational states. So I think that the tools in this area is still lacking, right? Is your guys' opportunity as well. So another important reaction is that CO2 hydrogen methylation. So this reaction is very interesting, and this is again is a lot of people studying this, and in UK and also in Europe. You can see that they basically using the fixed bed. This is that the catalyst. They put this kind of electrode, and they have a furnace to control the temperature, and then measure that the yield of methanation with CO2 and hydrogen. So this is at the exothermic reaction. So you can see certainly this heating is not a good thing. You know, if you exothermic, if you heat it, then the chemical equilibrium really is not good. But that CO2 conversion, you see that this is the equilibrium. And when you do this thermal and or DBD, you can get this a conversion close to 90%, which is very encouraging. So very high catalytic reactivity at low temperatures was confirmed because they also say because vibrational excited CO2, even though they did not really provide any evidence. It's just like knock the head and saying vibrational CO2 is going to be important. And the plasma give a maximum CO2 conversion of 87%, and methane selectivity is passing 99% at 300 C. So this is very encouraging. So everybody says CO2 plasma is not selective because the electron energy is broad. But here they say that the CO2 conversion is close to 90%, and then the methanation becomes 99% at a very low temperature. So this is a very encouraging thing that if some countries, some areas, they want to have a methane, and you have hydrogen and CO2, you want a methane, might be a way to do a plasma-assisted CO2 methanation reactions. So another reaction they draw a lot of attention is liquid fuels. How can we make a methanol oxygenated fuels so that it can for transportation on marine transportation and also ground transportation. And so that way you have CO2 and you have hydrogen, you can making methanol. So this is a metal catalyst. You can make methane and hydrogen. Why I don't understand why there's oxygen here, but oxygen you can do it too. So you can CO2, your plasma can break down that the CO2 to generate O atoms. This O atom and then and CO. The CO reaction with OH radicals and in hydrogen and the CO2 reaction, they form a COH. This Combustion group, then they can methanation into a alcohol. You can do a lot of things. But in this reaction, because it's exothermic, and it's very important to cool the electrode. So here is that people using water electrode to cool the electrode, increase the yield. So they can a lot of things if you're looking at the selectivity, and selectivity is quite low, it's about 30%. And also they produce a lot of kind of things. You can see that acetone, methanol, alcohol, acetic acid, a lot of things is producing. So the key question is that how can we identify a catalyst, a plasma catalyst, that increase that selectivity to a certain type of fuel can be produced? And how to improve that the conversion efficiency from today's 30-some% to more than 60% efficiency. So this is remain to be a very active research areas using a thermal catalysis and also that the plasma catalysis areas. So next thing you try to see that is to do is a chemical looping. So chemical looping, and a lot today, and I saw that one of the posters using iron to burn to generate energy conversion, burning ions. The chemical looping probably is a similar thing, that you have a metal here, and then you put air, you basically oxidize it, and and that metal oxide will transfer to a reactor that you have fuel like hydrogen or CO or something, or methane, that can oxidize into CO and CO2 without forming any kind of nitrogen in the stream, without forming NOx. So you can directly separate CO2 from hydrogen, and then you can do a separation on the CO2. So this has been pursued and in a long time. And National Energy NETL Technology Laboratory, they have a big demonstration plant, and they try to, to do this chemical looping. But chemical looping, so a lot of people using copper, and a lot of people using nickel oxide for chemical looping. And why is that? So if you're looking at chemical looping, that you can see this is iron, this is a copper, you see that the nickel, and both copper and nickel, when they do oxidation and reduction, they are both exothermic, right? So that helps that the process that to be used. And not only they are exothermic, and but also you can see that this is copper oxide. They can tolerate a certain temperature. So what is a major problem of copper oxide for chemical looping, even though nickel and copper has a good thing? So what are the problems of these two? Has anyone done chemical looping before? No one. So copper is a problem because they melt at a very low temperature. See what? And nickel is also a problem because they form carbon nanotubes. They just cover your surface, make you stuck. So that's why the chemical looping, the progress is quite slow. So if you're looking at the, so using a plasma reactor, for example, you will have a, dielectric barrier discharge. And so this is at the high voltage electrode, and this is the cathode. And you can, using that the grid as the electrode material, you can see that the plasma discharge is quite uniform if you spread that the copper oxide into that a wool. So you can molecular beam to detect that species and what kind of species generate. So one of the examples kind of show you that, for example, if you have a 1 gram of copper oxide and at a slightly lower pressure, and you flow methane into it with 99% of helium to dilute it. So what do you see from here? How much CO2 is formed as a function of temperature. So the black line is that I don't have a plasma, I'm just using thermal chemical looping. So you can see that you need to heat it around probably 400 to 500 Kelvin in order to make anything CO2 is oxidized. But if you have put a plasma, you can see that is quickly at around 250, that you can start to see CO2 is formed. At a very high temperature, 700 C, there's not much difference because that the thermal, just like I said, for flame, plasma does not help much if a high temperature flame. If the flame is near extinction or is ignition, plasma helps a lot. Here you can see the same, that if that is the CO2 conversion and at a lower temperature, plasma dramatically enhances the lower temperature by probably 200 degrees. And then at a very high temperature, you don't need plasma to do the job because oxidation is very fast. So if you're looking at the process, it's very interesting how CO2 is formed in, with methane in copper oxide. Initially, you have this very fast CO2 formation, and then your CO2 is reduced, and then CO2 is slowly formed. So we divide this into 3 regimes. The first regime, imagine you have a fresh copper oxide. You flow methane to copper oxide. And then the surface is so fresh. Then whatever methane can diffusion to the surface, and they will be oxidized. So this is clearly is that a diffusion limited. And then after that, the surface CO2 side is consumed, and then you are running into surface catalytic reaction limited. There's a lot of diffusion of methane to the surface, but you don't have a lot of oxygen site on the surface. So you are running this kind of a catalytic reaction limited regime. So afterwards, that all the surface of a copper oxide, they are consumed, oxygen is reduced. Then you rely on the oxygen inside of the core of the copper oxide to diffuse to the surface. So you have 3 different mechanisms. That's why you see a formation about a lot of formaldehyde formation in this region because many of the methane is not completely oxide. We have to wait for the diffusion of oxygen and from that the copper. So you can do a comparison between this reforming without plasma or with plasma. You can see at 300 Kelvin with plasma, you got a lot of CO2 form, and 400 Celsius also. This is at the copper oxide. So at low temperature, you see copper oxide and reduced to Cu copper 2 oxide at high temperature, and they go to the copper. So you can clearly see and the picture of the color of different. Again, what I try to say that using plasma, you can reduce that the chemical looping temperature, and so that enhance that oxidation process is one of the. So you can do some kind of a molecular dynamic simulation to see how much that the hydrocarbons and with the copper oxide, what is the reaction mechanism, for example, methane, and they become a methyl group, methoxy to methanol. And this all you can do in a molecular dynamic simulation. And you can do experimental measurement. You can see that you predict something is red, you never seen anything. And you observed, which is the yellow with the large hydrocarbons, but you never predict. And so this again open a weird, because this force field is not well developed. It's mostly using empirical molecular reacts FF, and it's empirical force field. So now is the opportunity for combustion people to put a high accuracy force field using machine learning and to do a ab initio based machine learning molecular dynamics to improve the prediction of the chemical looping. Anyway, so that I try to change the gear to another thing is a plasma-assisted ammonia synthesis. This is a big subject, and particularly in Europe, and probably in China too. And the United States is picking up, and so ammonia, everybody knows that is made by this Haber-Bosch process. They're using iron catalysts. They operate around, above 500 Celsius, typically 200 to 400 atoms, atmospheric pressure. Why do they want to do high pressure? It's because this reaction, you can see from chemical equilibrium, this is 4 more form 2 more. High pressure drives the reaction to the product. And why do they need high temperature? Because the nitrogen is so difficult to break down. The triple bond is so strong. You need high temperature, and you need the catalyst to do so, because the catalyst can reduce the temperature to 500 K. But this reactor, 200 to 400 bar, you require very large facilities. You really cannot design something small at home. And that may be very difficult to make it distributed. So therefore, if you make it smaller, the efficiency drop significantly. So what I'm trying to say, if you try to develop some kind of plasma process, if you can have 50% of the efficiency of Haber-Bosch, and then you are winning. Because when they scale down, their efficiency going down dramatically as well. So ammonia is a big thing when Professor Stephen Chu, when he took the position about Secretary of Department of Energy, and he came to Princeton to give a talk. He said, what is the biggest innovation in mankind history? And of course, he's a Nobel Prize winner. He got to say what he wanted to say. But he says ammonia, because it feeds the people in the world, right? We have how many people? 7 billion people in the world, right? 8 billion. And ammonia is the thing that makes the civilization and population grow. So there are 3 Nobel Prizes in this area, right? So if any one of you is interested in getting a Nobel Prize, this is one of the area might be possible. So you look at that progress about this from a recent progress of ammonia synthesis. 10 years ago, the people using ruthenium, magnesium, and ammonia catalysts, they reduced the activation energy from 100 kilojoule per mole. And 2020, they're using ruthenium, lanthanum, cerium oxide. They reduced to 60. And recently, they're using this ruthenium calcium fluorine hydride, and they reduce activation to 30. Significant progress, right? When you're talking about the combustion kinetics, 5% uncertainty, here is huge improvement, right? And so this is how it works. The earliest, and this is the invention of an ion catalyst and the Haber-Bosch process, win a Nobel Prize. And here that in 1970s, people using ruthenium, potassium, a catalyst, and then here the people using iron calcium hydride, ruthenium carbon hydride. The innovation keep going, and that give a lot of excitement about ammonia process. That help combustion people, because if the cost of making ammonia is cheaper, that means ammonia as an energy carrier become more viable, right? So I think that is a great thing to see. So how come plasma can do anything? And in terms of ammonia synthesis, we talked about that the electron impact, vibrational excitation, dissociation, and then vibrational dissociation, and then this LH mechanism. The dissociated nitrogen and hydrogen on the surface, that become a NH groups. So you can also do this kind of LA-Rideau mechanism that so N atoms is produced in the gas phase, and then the N atom on the surface react with the gas phase hydrogen to form a NH. Which one is important? In plasma process, everybody has a different opinion. And, but one thing for sure, this is electronic process. They require 5 to 10 electron volt. And you don't have a lot of electrons and in dielectric barrier discharge. But if we can drive the vibrational excitation, it only takes you about a few electron volts, and you can create a large amount of vibrational excitation. So therefore, there is an opportunity in plasma. How can you selectively vibrationally excite nitrogen, and so that it can cause in dissociation that improve the efficiency? This is a question, all right, and to many people. And then we don't have answers of it, so this is interesting. So Haber-Bosch process, they contribute about 1.6% of global CO2 production. And then the whole process is limited by gas phase nitrogen absorbed on two surface sites that become the surface absorbed nitrogen. And this is at the rate limiting reaction. And then if you can vibrationally excite molecular nitrogen, you probably can reduce energy barrier. But if you can create a new reaction pathway, this barrier can be further reduced to make that energy more efficient, right? So this is at the hypothesis. And then this is again trying to show you that the Nature Catalysis paper and published at Notre Dame University. They basically say that, okay, if you have a plasma off, and you just see that your, the turn-off frequency, this is a turnover frequency of catalyst. If you have a turn-on plasma, you see two changes. One, that the reaction rate is increased by 2 orders of magnitude at least. Second, the catalyst, ruthenium, you don't need it anymore. Nickel and cobalt basically can do the job. So this is a very encouraging calculation, and they published 2018. So since then, a lot of people inspired by this work, and they do a lot of experiment. Here is the result is my colleague, and we collaborate as a DOE Plasma Science Center. And he did the experiment. So this is a plasma, is a nanosecond plasma with 5 kilohertz, with 10% hydrogen in nitrogen, 90%, pressure lower, not a. So, and then the temperature is about 300 C, and to facilitate, say 500 C, 300 C is 200 C lower than the Haber-Bosch process. So what they say that a catalyst is just a nickel nitrogen catalyst. If you just turn on catalyst activation, and without hydrogen, you don't generate any kind of ammonia. Of course, that's true. Without hydrogen, you cannot. So now that you start to say, I turn on nitrogen and hydrogen with plasma, but I don't have catalyst. So you form some ammonia, that is 170 ppm ammonia. But now you say that I'm going to turn on catalyst and also plasma on, then I create about a double, 340. So plasma, in this condition, they say they can increase the yield by factor of 2. It does not come to the prediction about 2 orders of magnitude. And people start to understand why that the plasma cannot produce 2 orders of magnitude enhanced ammonia. Then what is the mechanism? Maybe the mechanism is wrong. And then last year, we did some kind of experiment and using hydrogen and nitrogen. We tried to understand how that the vibrational excitation of nitrogen and hydrogen, for example, this is that the hydrogen vibration, and then they indeed reaction with N atom, they form an H group, which is encouraging. That means that the vibrational hydrogen contribute to that energy coupling in the ammonia synthesis. And also you can see that from here that the nitrogen vibration also give you a new reaction pathway to an NH group. So this is great. But however, in a hydrogen process, if you have electrons react with a hydrogen vibrational state, and these reactions can generate hydrogen atoms and hydrogen negative ions, but this is the cross-section area. The cross-section area of hydrogen vibration, 1, 2, 3, 4, they're dramatically different. The question is that how can we enhance that, control the plasma to selectively create that hydrogen at a vibrational level of 4 and 5 and above 4, that will dramatically facilitate that process. So this is this kind of calculation, modeling, and then elementary chemistry, it gives you some hint what are the things that need to be done in this kind of plasma process. And then in terms of mechanism, the same group at Notre Dame, they published a paper 3 years later and saying that if you have a plasma, you can activate nitrogen without hydrogen at a low temperature, and then you increase the temperature, just flow hydrogen, and they found that a lot of ammonia is formed. So what the reason is that in the nitrogen process, the plasma create a nitrogen atom on the surface, and then you flow hydrogen, the nickel activate hydrogen, and they form hydrogen atom on the surface. This hydrogen atom react with a nitride and form a ammonia. And then that, they conclude that the nitrogen on the surface adsorption become a critical, is true. Well, they did a lot of experiments. We have to believe his rework. But is this the only mechanism? Right? That's it, being a researcher, you're always challenging to the result. Is this okay? This is good because you have to do the neutron scattering measurement. You see this NH group on the surface, which is great. But is this the only mechanism or not? And then we did some experiment with my student Hao, right now is in Beijing University. And what he did is that he's an ammonia conversion with this plasma with catalyst. And with empty catalyst with ceramic materials with a catalyst, what he sees is that there's no difference between whether it's with catalyst, without catalyst, or whatever Rusonian catalyst, cobalt catalyst, they got the same. So what do we conclude that this plasma gas phase chemistry that forms this NH, NH2, and NH, that provide a rate limiting reaction to the surface. So now they have two debates. NH group, that N atom, they become rate limiting. So which one is true, right? So I think this experiment, and I think that maybe there are multiple mechanisms to say so. Another mechanism we want to say that this is Aditya, I'm not sure he's here, is my postdoc right now, soon become professor at another university from September. I want him to understand that when you have a plasma, not only generate radicals and vibrational states, but also you create surface charges. If the surface is charged by electrons, and how would the nitrogen adsorption dissociation energy change? And he made this DFT calculation and says that if the surface is neutral, your adsorption dissociation energy is negative 0.62. And if the charge is a negative 0.48. It looks very small, but it's important because every EV is 11,000 Kelvin. So small change of EVs is a big change in terms of temperature. So if we do a simulation of a catalytic reaction about turnover frequency as a function of vibrational temperature, that means that the charge coupling with vibrational state of nitrogen, you're going to see that the reaction turnover frequency is 0.1, 0.2. This is increased by a factor of, significantly improved by this surface charge reactions. So the reaction rate is increasing with surface charge. That it maybe provide another mechanism. But more interestingly, that without charge, in thermal catalysis, you can see that the hydrogen adsorption dissociation energy and the nitrogen adsorption dissociation energy with a certain catalyst, they have a very good correlation. You see that ruthenium, platinum, iron, cobalt, and what if you put a charge on the surface? Does the same correlation still hold? And then the calculation basically show is completely different. Then when you have a surface charge, ruthenium is here, platinum here, iron is here, cobalt is there, and nickel is there. So they have very different adsorption energy correlation, different from equilibrium. So what does it mean? It means that if you use in plasma, you can manipulate the surface charge. Your catalyst surface adsorption dissociation relationship derived from thermal catalysis may not be applied to plasma catalysis, which is a good sign. Good sign means that they give you opportunity to explore plasma catalysis. They may not be the best thermal catalysis. So that is giving you a research opportunities. And then another group in UK, and they did this kind of, so the plasma, you generate ammonia, but then the next electron will break down the ammonia back to the hydrogen and NH. That's a problem. And using this kind of a MCM, the metal complex materials, that if you have a plasma, you create this ammonia. This ammonia is going to penetrate this porous materials, diffuse the channel, and diffuse out. So by doing this, and he said with this materials with the nickel, they can increase the yield by a factor of 2. So you can see that this is at the frequency, and then it can increase the yield by 2 by using materials. So therefore, this provides another hint that if you, not only that you can control that the ammonia synthesis, but also that the ammonia synthesis, the ammonia form can be stored and transported out, that increase the yield. And then, so recently in Europe, I think that this Europe, and people try to combine the electrochemical process. They split water into hydrogen, and these hydrogen protons, they move to the right, and on the right side you have plasma, and that plasma just create that a chemistry react with the proton and form ammonia. So this reactor, you put it into the reactor, is a BCZY. They probably zirconium, yttrium zirconium, baryons, membranes, but this require very high temperature. And they saw ammonia, but you can see the paper, the published ACH energy letters. This kind of journals, and very difficult, very high citation impact, but they love this kind of ammonia stuff, but this is a high temperature process. It is good, but the efficiency remain a question because that you need a very high temperature to activate this membrane. The question that can we design a membrane that work around room temperature, that can diffuse this proton to the other side that allow me to do this ammonia synthesis? Well, that is another open question, right? It's very interesting. And That is a proposal I'm working with Aditya, and try to submit it to DOE. And we come up with an idea and materials, plasma, we can do it. So you always has a problem. It's always an opportunity to us to stimulate our thinking. So I will stop here. Let's take a break and then come back to about how do we make ammonia from NOx.